Now I'll define orthogonal complement. Let big U be a subspace of big W. Then for each vector B in big W, we can break it up into its parallel part and its perpendicular part. The parallel part is the projection of B onto the space big U, and the perpendicular part is the projection of B orthogonal to the space big U. Note that B parallel is in big U, and B perpendicular is orthogonal to big U. That is, it's orthogonal to every vector in big U. So we can take every vector B in W and split it up this way. And we'll define big V to be the set of B perpendicular obtained this way, taking all the vectors B in big W. And we call this set big V the orthogonal complement of big U in big W. Now, it's easy to see that every vector in big V is orthogonal to every vector in big U. That's how we constructed it. Also, every vector B in big W can be written as the sum of a vector in big U, the parallel part, plus a vector in big V, the perpendicular part. Now, the second condition, that every vector in big W can be written as the sum of a vector in big U plus a vector in big V, suggests that maybe there's a direct sum here. So that raises the question, is big W the direct sum of big U and big V? Well, for the direct sum to even be defined, it has to be the case that big U and big V share only the zero vector. So let's see if that's the case. So consider any vector W in both big U and big V. It must be orthogonal to itself. It has to be both the parallel part and the perpendicular part. So that means the inner product of W with itself is 0. But the inner product of a vector with itself is the square of its norm. By a property of norms, if a vector has norm 0, it must be the 0 vector. So that shows that the only vector common to U and V is the 0 vector. And so direct sum is in fact defined. And because of this property, big W is the direct sum of big U and big V. Now remember that that means that the dimension of big U plus the dimension of big V equals the dimension of the inner product, U plus V, which is W. So here's an example. Let big U be the span of these two vectors, and let big V denote the orthogonal complement of U in R4. What vectors form a basis for big V? Well, by looking at these generators, we can see that any vector in big U has its first two entries the same and its last two entries the same. So it has the form AABB. So any vector of the form C minus C, D minus D is orthogonal to every vector in big U. So let's consider the space spanned by these two vectors. Every vector in this space has this form, C minus C, D minus D, so is orthogonal to every vector in big U. So we know at least that the span of these two vectors is a subspace of big V, the orthogonal complement of big U. Is it, in fact, the whole thing? Is it all of V? Well, we know that the direct sum of U and V is R4. So the dimension of U plus the dimension of V is the dimension of R4, which is 4. Now, these generators for big U, they're linearly independent. So that shows that the dimension of U is 2. Plugging that in, we see, therefore, that the dimension of V is 2. Now, these two vectors, in fact, are linearly independent. So the dimension of their span is 2 as well. So that shows that, in fact, this span covers all of big V. So it's equal to big V. So we found the orthogonal complement of U in R4. So here's a use of orthogonal complement. Our goal is to find a basis for the null space of a matrix. Now, by the dot product definition of matrix vector multiplication, a vector v is in the null space of this matrix if the dot product of every row with v is 0. So that tells us that the null space of this matrix equals the orthogonal complement of the row space in R4. Now, these three rows are linearly independent. So the dimension of the row space is 3. We know the dimension of R4 is 4. So the dimension of the orthogonal complement is 4 minus 3, which is 1. And now here's a vector that has a dot product of 0 with each of these rows. So this vector forms a basis for the orthogonal complement. It's definitely in the orthogonal complement, and the space it spans has the right dimension. So the space it spans must, in fact, be the orthogonal complement. So we found a basis for the null space of this matrix A. Let's use these ideas to find the intersection of two planes. We take this plane, the plane spanned by these two vectors, and this plane, the plane spanned by these two vectors, and we want to compute the intersection. Well, the orthogonal complement in R3 of this first plane is the span of this vector. That shows that the first plane equals the set of x, y, z, such that this vector dotted with x, y, z is 0. Now, the orthogonal complement in R3 of this second plane is the span of this vector. Therefore, the second plane is the set of x, y, z, such that the dot product of this vector with x, y, z is 0. Therefore, the intersection of these two sets is the set of x, y, z that satisfy both conditions. This dot product is 0, and this dot product is 0. Okay? So we've expressed this essentially as the null space of a matrix. By the row space null space duality, a basis for this vector space is a basis for the null space of this matrix. Notice that the rows of this matrix are the vectors in this formulation of the set. And the null space of A is the orthogonal complement of the span of its rows in R3, which we can determine is the span of this vector. That shows that the intersection is the span of the vector 1, 2, minus 2. How would we actually compute the orthogonal complement? Suppose we have a basis, u1 through uk, for the vector space big U, and a basis w1 through wn for the vector space big W. How can we compute a basis for the orthogonal complement of big U in big W? Note that here we're assuming that big U is a subspace of big W. One way is to use orthogonalize. Apply it to a V-list consisting of first the vectors u1 through uk that form a basis for big U, followed by the vectors w1 through wn that form a basis for big W. This seems like a strange thing to do because, after all, the vectors u1 through uk are already spanned by the vectors w1 through wn. The vectors u1 through uk lie in big U, which is a subspace of big W. So it's counterintuitive to include them in this list. But you'll see why we need them. Now, the output of orthogonalize is a list of vectors I'll write as u1 star through uk star, followed by w1 star through wn star. And these span the same space as the input vectors. The space spanned by the input vectors is exactly big W. Big W has dimension n. We see that it has a basis of cardinality n. These span the same space. Therefore, they span big W. So the space they span also has dimension n. We saw earlier that the non-zero vectors in the list output by orthogonalize form a basis for the space spanned by the input vectors. So the non-zero vectors in this output list are a basis for an n-dimensional space. Therefore, there must be n of them. So the number of non-zero vectors in the output is exactly n. Now, the vectors u1 star through uk star span exactly the same space as the input vectors u1 through uk. And they are all non-zero vectors because u1 through uk are linearly independent. They form a basis for big U. So they account for k. So u1 star through uk star account for k non-zero vectors in the output. So exactly n minus k of the remaining output vectors, w1 star through wn star, are non-zero. Now, every one of those output vectors is orthogonal to u1 through un. So they're orthogonal to every vector in big U. So they lie in the orthogonal complement of big U. Now, by the direct sum dimension lemma, the dimension of the orthogonal complement is n minus k. So those remaining non-zero vectors among w1 star through wn star are exactly a basis for the orthogonal complement.